Hey everyone, this is Bhargav Sudhar, and today we are going to learn what is a recurrence relation. So in this today's session we will discuss what is a linear recurrence relation and what is a homogeneous solution, or how to find a homogeneous solution. So first let's understand what is a recurrence relation. In many discrete computational problems, it is easier to obtain the numeric function from the relation between its terms. So the recursive formula for defining the numerics function is called a recurrence relation. So consider a numeric function a equals to a0, a1 up to ar. So consider this numeric function. Then recurrence relation on the numeric function a. It is a function that relates all the terms of a to previous terms of a. So it is also called a difference equation. So a recurrence relation is also called a difference equation. Now to define the numeric function completely using the recurrence relation, the values of the numeric function at one or more points are required to initiate the computation. So for computation, 2 or 3 points values will be required. Now these values of the function are called initial conditions. So for example, now the recurrence relation for Fibonacci sequence of numbers, and that is given by this AR equals to AR minus 2 plus AR minus 1, where R is greater than or equals to 2, with the initial condition A0 equals to 1 and A1 equals to 1. Now we all know that what is a Fibonacci sequence. So the Fibonacci sequence will be given by like this: 1, 1, 2, 3, 5, 8, 13. How? See, we have here the initial conditions are A0 equals to 1 and A1 equals to 1. So if we put R equals to 2, so the equation will become A0 plus A1, so that is 1 plus 1. So 1, 1 and 2. As the initial conditions are all already there, so 1, 1, 2, then again 1 plus 2, that is 3, then again 3 plus 2, that is 5, and so on. This is how you can construct a Fibonacci sequence. Now let us understand what is a linear recurrence relation with constant coefficients. So suppose R and K are non-negative integers, and a linear recurrence relation of the form this C0 plus AR plus C1 AR minus 1 plus C2 AR minus 2 up to CK AR minus K, and that is let us take one function f of R where R is greater than or equals to K. Now where this C0, C1 up to CK are constants, and they are called linear recurrence relation with constant coefficients of order K, provided this C0 and CK, that means the first term and last term, has to be non-zero, otherwise it won't work. So for example, the relation AR minus 2AR minus 1 equals to 2R is a first order linear recurrence relation with constant coefficients. See how here in this general equation AR minus K, so R minus K, that means so it is of order K. So here we have R minus 1, so just compare it with R minus K, so you will get K equals to 1, so hence it is a first order linear recurrence relation. Now in same manner, let us take AR plus 2AR minus 3 equals to R square. Now this is a third order linear recurrence relation. Why? Because we have here R minus 3, so it is a third order linear recurrence relation. Now AR square plus AR minus 1 equals to 5. That is not a linear recurrence relation, because in the general form we have only AR or AR minus 1, but here in the example we have AR square, so that won't work. So it is not a linear recurrence relation. Now let us understand what is a homogeneous solution. So consider a kth order linear recurrence relation with constant coefficients. So just consider this equation that we have discussed. So C0 AR plus C1 AR minus 1 plus C2 AR minus 2 up to CK AR minus K equals to f of R, and where R is greater than or equals to K. Just consider this equation number 1. Now then the homogeneous recurrence relation of the above recurrence relation, that is given by C0 AR plus C1 AR minus 1 up to CK AR minus K equals to 0. Now what is the difference between this equation and the previous equation? You can see that there is only one difference, that f of R equals to 0. So that means for any linear recurrence relation, if f of R equals to 0, that means the right hand side equals to 0, then the given equation is homogeneous linear recurrence relation. So whenever right hand side equals to 0, then we can say that it is a homogeneous recurrence relation. So, and the solution of that equation is called homogeneous solution. Now, the characteristic equation of the first equation is the kth degree polynomial, and that is given by like this: C0 alpha raised to k, because the order is k, so we will start from alpha raised to k. So C0 alpha raised to k plus C1 alpha raised to k minus 1 up to Ck equals to 0. So this will be the characteristic equation. Now the polynomial in alpha is of degree k, yes, obviously, so it has how many roots? K roots, and it is called the characteristic roots. Now let us understand the types of roots. Now let alpha 1, alpha 2 up to alpha k be the roots of the characteristic equation. Then there will be how many? There will be total 2 possibilities. So the first one, there can be distinct roots, or then can be multiple same roots, or 2 equal roots, or it can be 3 or 4 and so on. So for distinct roots, the general form of the solution will be like this: AR equals to A1, whatever the alpha we have found, so alpha 1 raised to R plus A2, alpha 2 raised to R up to AK alpha k raised to R. And for 2 equal roots, we are just combining these 2 constants, so that is A1 plus A2R into alpha 1 raised to R plus the rest of the terms are same, so A3 alpha 3 raised to R up to AK alpha k raised to R. So let us take examples. So find the solution of AR plus 2 minus AR plus 1 minus 6AR equals to 0. So first, see, the characteristic equation will be like this. First, just determine what is the order of the given recurrence relation, and also you can see that here right hand side equals to 0, so that means it is a homogeneous linear recurrence relation. So the first characteristic equation will be like this: as we have R plus 2, so the order will be 2. So we will start from alpha square minus alpha minus 6 equals to 0. Now it is a quadratic equation, so you can solve very easily. So the factors will be alpha minus 3 into alpha plus 2 equals to 2. So what will be alpha? So alpha will be either 3 or minus 2. Now you can see that 3 and minus 2, they are the different roots, and also they are the characteristic roots. So the first case will be applied. And what is the first case? If we have distinct roots, so the homogeneous solution for the recurrence relation will be this: AR equals to, see, A1 alpha 1 raised to R plus A2 alpha 2 raised to R. But see, here you can take alpha 1 and alpha 2 any numbers. So that means if we take alpha 1 equals to 3 or alpha 1 equals to minus 2, it won't change the answer. So AR equals to A1. Here we have taken alpha 1 as 3. So A1 3 raised to R plus A2 minus 2 raised to R. As we have only 2 roots, so we will just stop here. So AR will be this. So this is the homogeneous solution. Now let us discuss second example. Find the solution of this AR plus 2 plus 2AR plus 1 minus 3AR equals to 0, and that satisfies A0 equals to 1, A1 equals to 2. So here the additional term or additional data is, we have given some condition, that is A0 is 1 and A1 equals to 2. Now the first we will write what is a characteristic equation. Now here you can see that what is the order of the equation, and also it is a homogeneous equation, so the order here, the order is 2. So the characteristic equation will start from alpha raised to 2 or alpha square. So that is alpha square plus 2 alpha minus 3 equals to 0. Now again it is a quadratic equation, so we need to solve it. So what will be the roots of this equation? So that is the alpha plus 3 dot alpha minus 1 equals to 0. So that means alpha will be this minus 3 and 1. So which are the characteristic roots of the equation? Now as you can see, they are the distinct roots, so we'll consider the first case. So the homogeneous solution of the given recurrence relation, it will be like this: AR is A1 alpha 1 raised to R plus A2 alpha 2 raised to R. Okay, but here we are taking alpha 1 as minus 3 and alpha 2 as 1. So AR will be A1 minus 3 raised to R plus A2 1 raised to R, where A1 and A2 are constants. So this will be the homogeneous solution. But see, here we have given A0 equals to 1 and A1 equals to 2. So we will use that condition, and also we will find what is the value of A1 and A2. So now put R equals to 0. So what we will get? So we will get A0 equals to A1 minus 3 raised to 0 plus A2 1 raised to 0, and that will give A0 equals to A1 plus A2. So also put R equals to 1 in that solution, so we'll get A1 equals to a1 minus 3 raised to 1 plus a2 1 raised to 1. So that will lead to a1 equals to minus 3a1 plus a2. Now if you solve this equation by using whatever the method you know, so a1 will get minus 1 by 4 and a2 will get 5 by 4. So just substitute the values in the solution, so we'll get AR equals to, here it was a1 minus 3 raised to r, so that means minus 1 by 4 into minus 3 raised to r plus 5 by 4 into 1. So that is the final answer. Let us discuss another example. Find the solution of AR plus 6AR minus 1 plus 12AR minus 2 plus 5 plus 8AR minus 3 equals to 0. Now again, here right hand side equals to 0, so it is a homogeneous equation. Now we will write what is the characteristic equation. Now see, what is the order of this equation? Here we have r minus 3, so that means the order will be 3. So let us start with alpha raised to 3 or alpha cube. So alpha cube plus 6 alpha square plus 12 alpha plus 8 equals to 0. Now it is a cubic equation, so the factors will be like this: alpha plus 2 cube equals to 0. So alpha will be minus 2 minus 2 minus 2 3 times because we have cube, so it is repeating 3 times. So the homogeneous solution will be like this. See, here we have the root that is repeating 3 times, so the solution will be a1 plus a2r plus a3 r square into alpha raised to r, because all the alphas are same, so minus 2 raised to r. Suppose it repeats 4 times, so the solution will be a1 plus a2r plus a3 r square plus additional a4 r cube into whatever the alpha raised to r, where this a1, a2 and a3 are constants. So this will be the final solution in the case where the roots are repeating. Thank you.